Hey y'all, welcome back to my channel. And today we are going to do some math problems. So let's get into it. We're going to start a new lesson, which is called Radical Ideas. And it's about like a radical, and a radical is this guy right here. See this guy right here? Do you see him? That is what a radical is. So I'm just going to do a couple of reminders first before we get started. It says if n is a positive integer greater than 1, and both a and b are positive real numbers, then all of these things are true. Okay, so first of all, let's just talk about the definition. The square root of a number squared is that number. Okay. The square root of a number squared is that number, because it's essentially they are undoing each other. In math land, we call that they are inverses of each other. So they kind of like, you guys would say something like they cancel each other out, Miss Johnson. Exactly. So here again, both a and b are positive real numbers. If you're wondering, because some of you wonder these things, and I love that you wonder these things. You're like, what if it wasn't positive, Miss Johnson? Do these rules still apply? Kind of, but in a different way. And you will learn more about that next year when you learn about quadratics and stuff. So just hold on. So number one, if you have the square root of a number, or an nth root of a number in this case, you can break it down into the nth root of a times the nth root of b, which is how I break down square roots. Okay, let me show you what I'm talking about. So when I'm here and I'm thinking about, hey, what's the square root of, I don't know, let's do 144, right? We know what the square root of 144 is, so that's why I'm specifically using 144. So when I break down square root of 144, I break it down into its parts. So, hey, what times what gives me 144? What times what gives me 144? Yes. So someone says 12 times 12, Miss Johnson, and I'm going to say yes. And if you said like 9 times something, or even if you said 2 times 72, that works too. Okay. And so the way I do this, and I would, once I found a pair, then I would stop. But I'm just going to show you so you guys can all see how I break down square roots. So then I would continue and I would say, okay, well, what times what gives me 12? And someone's like, 2 times 6. And then I will stop when I get to a prime number that doesn't break down besides 1 in itself, right? So then 6 would be 2 and 3. So I'm going to copy that over here because that's exactly the same. So the first thing I'm going to do is I'm going to pull everybody down so they're all on that same level. And so this is the funny part, and I never thought about this until I was explaining this to my integrated 3 students. And I'm like, do you see how it's like kind of a tree and it's upside down? And then they're like, yeah. And so this is one way to organize your word. Yeah, exactly. This is actually called factorization. Very good. So someone's like, yeah, Miss Johnson, or it could be the roots of a tree. Get it? And I was like, oh my gosh, you know how long I've been doing this? And someone's like, that looks like the roots. Yes, a pyramid as well. Exactly. So I just thought that was neat. So when you're simplifying this, you're looking for pairs of stuff, pairs. So only look at this bottom row here. Does anybody see a pair? What do you see a pair of? And someone's like, oh, Miss Johnson, I see the 2s. Exactly. So for every pair, I write it on the outside. For every pair, I write it on the outside. Does anybody see another pair? Ooh, someone says 6s. I'm going to ignore the 6s just because they're up here. I'm always going to look at the bottom row just because. Yeah, and someone says the 3s, Miss Johnson, and someone else said the 2s. Now, here's the thing. Someone would say, Miss Johnson, I get the 3s, so let's circle that. And then someone says, Miss Johnson, is this 2 the same as this 2? And I'd say no, because look, they're separate. So I would write them separately as well. And look at that, 2 times 3 times 2, oh, it's going to show up soon. 2 times 3 times 2 is in fact 12. So isn't that awesome how we already knew that the square root of 144 is 12? It's going to show up one day. It is 12. I know. Wow. Math, right? It's really not going to show up. Okay, so no matter which way you do it, it should make sense. And so again, this is the reason why I like math so much, is because if I did it this way, or if I did it just because I knew the square root of it, I'm validated because the answers came out to be exactly the same, right? Woo, woo. Okay, so let's move on to our next little guy. Okay, and then here, if you're taking the square root of a function, and I keep saying square root, just because I want you to have like an understanding that it applies to all roots. So n would be any number like 7, the 7th root of some fraction is going to be the 7th root of the numerator divided by the 7th root of the denominator. Okay, so it says, illustrate each of these rules with an example using numbers. We're kind of doing that here, but we'll kind of move on in just a second. Actually, we did this one. We did B right here. And then it says, show why each of these rules is true by rewriting the radical expressions using rational exponents. And this is the part that's important that I want to get to. So let's go over here. So first it says, illustrate these rules with some radicals. And this one right here, could someone give me a number? Can someone give me a number? Good. So, and then can someone else give me a power that you want me to raise it to? Perfect. Someone said 32. I'm just going to go with 32. So if I take 21 to the 32nd, and then I take the 32nd power of it, the 32nd root of it. Hold on, just wait for it. Wait for it. Yeah. Oh, it's still not there. Just imagine a little 32 here. Do you see how they undo each other? So let's go with a smaller number just so we're all on the same page. If I said 4 squared and take the square root of 4. If I said 4 squared and then I took the square root of 4. There it goes. So these two will undo. I will like cross these out so everyone sees that they undo, and this is just 21. Let's just test this with an easier number. Hey guys, what's 4 squared? What's 4 squared? Very good. It's 16. And what's the square root of 16? Exactly. It's 4. So do you see how this 4 is this 4? Do you see how this 4 is this 4? Ta-da, we did it, right? So we proved this rule, not proved, we showed an example of that. The same thing would go here, okay? So really quickly, I don't know, I'm going to do maybe the cube root. The cube root of, I don't know, 8 over 27. So that means it's the cube root of 8 over the cube root of 27, which is just 2/3. Okay, cube root means what times itself gives me 8. And you try 1 and you're like, 1 times 1 times 1 is 1. Nah, try 2. 2 times 2 times 2. Oh, that's 8. Do you all see how that works? Oh man, we're really, really laggy right now. That's not good. All right, there it goes. Okay, so then you would separate them out and do the cube root of the numerator and then the cube root of the denominator, right? And then you would have your answer. Okay, so this is going to show up, I promise. The next part says, show why each of these rules is true by there it goes, by rewriting the radical expressions using rational exponents. Now look, what they're saying here is like the cube root of a fraction is the cube root of the numerator divided by the cube root of the denominator. Okay, it wouldn't, if you did it this way, or if you did it this way, you would still end up with the same answer of 2/3. Okay, So if I take 2/3 and I cube it, it would end me up back over here with 8/27. Okay, so this one, they just want you to show that these rules are true based on the radical expressions using rational exponents. So they just want you to rewrite these. So I'm going to do the first one with you. So the first one says a to the n, and then the nth root of that. Well, earlier we learned that if we have the nth root of something, we could rewrite it as a fraction. As a fraction. So I'm going to remind you over here really quick, right? So we have, like, let's just say 4 to the 1/2 is equal to the square root of 4. 4 to the 1/2 is equal to the square root of 4, because this invisible 2 right here is that denominator right there. Does that make sense? So can you rewrite this using a fractional exponent for this radical right here? Give me 1 second. I mean, I'm going to give you a couple seconds to do that. Go ahead and try. Okay, so I'm going to make this match this. So I'm going to take this over here for just a second. It's the power of digital ink. It's my favorite. So what I'm going to do is I'm going to copy this and apply it so that I could rewrite this. So I'm going to write it here, equals 2. Now look, 4 matches with 4. So what's my base going to be? Very good. Sorry, I'm just writing down something. Very good. It's still as your base. So what's your base going to be? It's going to be A. Everybody okay with my base being A? So 4 matches with 4. A matches with A. Okay. Now, where did this guy's called the index. Where did this little 2, where did this 2 go? Where did it go? Yes, it went in as the exponent, as the denominator. Very good. So what am I going to write here? What do I write here? Yes. Someone said it got reciprocated. I like that idea. It got reciprocated, right? It got flipped on and is now doing a handstand, right? So it's not just n, it's to the one n. So this n here goes here, right? This n goes here. But Ms. Johnson, what about this n? Well, he just stays with your a. He just stays with your a. Does that make sense? Okay. So I just wanted to use that to write that. Good. So does everyone see how that works? So this n, this is the most important part, is that n. That n is that n. Okay. Now they wanted you to prove that it equals to a. What did you all just tell me that I do with these exponents when it's a power to a power? What do I do with these exponents when I have a power to a power? Yes, very good. We multiply. So I know it feels funny because we're working and going left, and normally we work towards the right, but that's okay. We're just going to keep going. So you want me to multiply my exponents? Yeah, n times 1 over n. What is n times 1 over n? What is n times 1 over n? What happens to these? Now let me write it up here just so that you guys all see. What's n times 1 over n? This is fraction review, right? Very good. Very, very good. So fraction review says, I'm going to pull you back into like 6th grade when you were multiplying fractions. And when we multiplied fractions, we multiplied top times top and bottom times bottom. Yeah. Oh, is that true? That's cool. So top times top and bottom times bottom, that's n divided by n, which is just 1. So you're saying, Miss Johnson, this is a to the first. That's exactly what we're saying. Look, you just proved that rule. or oh, it's not called proved. You generated, you see why that rule is true. Okay, very good. So that's that one, right? That's that one. Excuse me. For this next one, when we want to prove that same very similar thing, we're going to do the same thing here. And you should remember, kind of like what we were doing over here, to build this understanding. Does that make sense? Excuse me. Okay. So hold on a second. I need to cough. Okay. So now we're going to prove that second rule, which is the nth root of a times b equals to the nth root of a times the nth root of b. I will tell you right now, when you're doing like proofs in math, there's a couple of different ways that you do it. And one way to do it is we go like this, right? We start with this and we end here. Or we start with this and we end here. Now, this is going to show up if my computer's just a tad laggy right now. Okay. So here, the very first step that I'm going to go with is I'm going to rewrite this using my fractional exponents. So tell me again, where does this n go? Sounds good. Thanks for letting me know. Where does this n go? It says an exponent, so it's 1 over n. All right, I got to hustle here. So this means, and if you remember this rule right here kind of looks like this. I'll show you over here. It looks like this. Remember when you had like x squared times, maybe I'll just go 4x squared, and then you cubed it. Do you remember doing this? And you would say, oh, that's 4 cubed times x squared cubed, because if we rewrote this 3 times, we'd have 4x squared times 4x squared times 4x squared. Collect the 4s, you get 4 cubed. Collect the x squareds, you get x squared cubed. So that's times 3, right? So here, you're just going to apply that exponent to all of your bases. So here, this is going to look like a to the 1nth times b to the 1nth, right? Okay. Which, by the way, that is just that, right? When you see a fractional exponent, your brain should say, oh, Ms. Johnson, she taught me this. That means it's the nth root. Same thing goes here. Oh, that means it's the nth root. So do you see how we went from here to here to here, and now we're here? Very good. Very, very good. This is where I'm going to pause the video for now, and then we're going to come back and finish up the rest of this lesson.